Hi, my name is Jason Franz. I'm an associate professor in the Joint Department of Biomedical Engineering, and I'm also the director of the Applied Biomechanics Lab here at UNC Chapel Hill. Our laboratory, which is comprised of undergraduates, graduate students, medical students, and postdocs, seeks to understand the neuromechanics of walking ability limitations and falls. In other words, we try to understand the neural and biomechanical basis for the loss of walking ability and the exceptionally high risk of falls so that we can introduce new and more effective clinical countermeasures to preserve and restore independence and mitigate that risk of falls. In the lab, our experimental and computational work is highly interdisciplinary. On the experimental side, we combine three-dimensional quantitative motion capture with treadmill force ergometry, electromyographic recordings of muscle activity, and non-invasive in vivo ultrasound. Our experimental approaches are quite diverse. If you see them in the lab in a moment, we have, for example, a suite of balance perturbation paradigms to challenge balance while we take our quantitative measurements. Then we integrate the experimental work with computational work, where we're using state-of-the-art computational and musculoskeletal modeling and bioenergetic simulation, as well as deep neural networks to do advanced data analysis.
Hi, I'm Becky. I'm a postdoc in the Applied Biomechanics Lab, and the research that I work on investigates age-related changes in muscle-tendon interaction and how those changes affect mobility in older adults. Today we are markering up a subject for 3D motion capture. As you can see, she's wearing a lot of reflective markers all over her legs and torso, and these markers are captured by the infrared cameras around the room, and they pick up her 3D position of the joints and segments. She's also wearing a metabolic mask, and from this we can estimate her energy expenditure while she walks. And today the task she's going to be doing is looking at this screen, which will have a virtual reality on it that moves back and forth and so may perturb her walking, and we can capture her reactions in real time.
So what we just saw is Mandy walking on our treadmill, responding to optical flow balance perturbations and the safety of virtual reality here. Now, Mandy is a young adult, otherwise healthy, and so her response was rather muted. But imagine if we had one of our patient populations in the lab, if we had a person with neurodegenerative disease like multiple sclerosis, or even an otherwise healthy older adult. What you can imagine is standing behind the person, that person would be moving side to side a lot more. They'd be exhibiting crossover steps as they try to preserve their balance from one step to the next and not fall. And that's really the goal of this, for example, as a diagnostic test. You have these individuals walk normally, and you don't see a lot of differences in their balance during walking. And it's only when we disrupt their balance, for example, through the use of optical flow perturbations, that we bring to the surface those preclinical balance impairments that we would expect to precipitate a first fall.
My name is Billy Clark. I'm a fifth-year PhD candidate at UNC and NC State working with Dr. Jason Franz in the Applied Biomechanics Lab. So one of the major goals in our lab is understanding age-related changes to walking ability. So I think one of the most rewarding parts about this research is we get to show that community of older adults what we're doing to get at that question of how does walking ability change with age, what are the underlying tissues responsible, and what are we doing to try to further investigate this question.
All right, so right here what we have is an ultrasound imaging device to place over the subject's right calf muscle. And what that does is it allows us to view the contractile behavior of the muscle while they're walking so we can see how that changes with different conditions.
Okay, what I showed you earlier was us using ultrasound imaging to look at the muscle contractile behavior of calf muscles. And what we can do is we can actually place a second ultrasound transducer over the Achilles tendon to simultaneously track muscle and tendon behavior. And that's really important because muscle and tendon behavior changes with age and impacts walking performance. So on the right, we have a video showing the tissue behavior of the Achilles tendon during walking, and we can splice that together with muscle in real time. In our lab, we work with a lot of undergraduate researchers. We consider them an integral part of our team. In fact, even some undergraduates have led their own research efforts in our lab.
I work with one undergraduate student, Callum Funk, and he has been researching deep learning methods for automated tracking of muscle tendon junction and of muscle fascicles during walking and other dynamic activities. And his efforts have actually led to a recent publication that we just submitted. So he's been super productive, and we're really happy to have him in the lab.
Hi, my name is Mandy Munch. I'm a third-year PhD student in the Applied Biomechanics lab. For my undergrad degree, I actually studied neuroscience, and then after graduating, spent a few years working in the neurobiology department, and then made my way over here, and now I'm studying gait biomechanics in the biomedical engineering department. I really enjoy the split that I get to have as a graduate student. Some days I'm in the lab working with participants, and some days I'm deep into the data working on MATLAB code or some of the other software that we use. I'm passionate about preserving independent mobility and physical activity following knee injuries. I have a few projects going on at the moment. For one of them, I actually collaborate with the Human Movement Science group over in the Exercise and Sport Science department over at Fetzer. And for that, we're bringing in people with ACL reconstruction, and we are helping them manipulate the way they walk. So they follow biofeedback that measures how hard they are pressing on the ground when they walk, and the idea is that by changing the way they walk, they're manipulating the forces that their knee experiences.
The work we do lends itself well to collaboration across the department within biomedical engineering, but also outside of that department with physical therapy and exercise and sports science, with geriatrics and neurology and orthopedics and computer science. It's really by integrating those large, diverse groups with various backgrounds and experiences that we feel we can make the biggest impact to address the science and engineering questions that we have in our field of biomechanics.